Welcome to this Desktop Metal webinar, talking about the manufacturing the cars of tomorrow. We're here with Jonah Myerberg, Desktop Metal CTO, to talk through some of the exciting new things on the horizon when it comes to manufacturing in the automotive industry. As we talk through some of these points, be sure to put your comments in the chat below, and we'll take a few minutes at the end of the show and go through and answer those questions. So to start off, Jonah, can you tell us a little bit about your background in the automotive industry, kind of where you came from to get to Desktop Metal, and how that might relate to some automotive things we're talking about?
Sure, yep. So I'm a mechanical engineer by degree, and I think like most mechanical engineers, we are attracted to the automotive space. It's exciting. Cars are a feat of engineering marvel. It's really, they're really an attractive machine. So I've been fortunate enough to work with a number of the large high-performance automakers as well as the large OEMs around the world. So part of my past history, I was designing batteries for automotive industry, for the electric vehicles, for hybrid vehicles, plug-in hybrids, start-stop hybrids, as well as high-performance hybrids like Formula One and WEC, the Le Mans cars, the endurance racing class. And then I worked with some Formula E teams on putting some batteries in place in that space as well. So a lot of exciting high performance applications as well as road car.
Cool, very cool. So Jonah, to start off, can you tell us a little bit about like how automotive parts are typically manufactured today? Like what are the processes people go through to actually make parts that go in cars?
Oh yeah, so there's a variety. It's all across the board. Matter of fact, one of the things you learn as an engineer in school are the different types of manufacturing technologies out there that you can pick and choose from as you're designing parts. So as you're forming metal or plastic, you can choose from dies and molds, stamping operations, and in vehicles we tend to see all of them. They're a sheet metal assembly that is made from numerous parts combined to create the frames of a vehicle, or castings or forgings to create the suspension systems or the engines of the vehicle, as well as powdered metal to create some of the gears or smaller components. So there's metal throughout the car, and then polymers as well, just as much of a variety there.
Awesome. So obviously it seems like there's a lot of different ways that you're able to make parts. But what are some of the issues with those current ways of manufacturing? Something as an automotive engineer you run into when designing these parts? Yeah,
and all manufacturing processes have limitations, and certainly in the automotive space, it's not an exception. One of the things that you try to do with any type of product design is you try to lock that design down so that you can produce a high volume of that design. And when you do that, you tend to invest in tooling, and you invest in high volume manufacturing processes, which makes you less flexible, but it also increases your production and productivity. So for example, you might design a cast or a forged part, and you might invest in the tools that create that part. Now you've locked yourself into a manufacturing process that you need to design around. So for example, a casting would require an open and closed type of design where the mold creates the part, which means that the part needs to be drafted to come out of the mold. It can't contain undercuts inside of the part that would prevent the part from ejecting from that mold. The same is true for a stamping operation. So let's say you're creating some metal components that you want to make out of a sheet steel. That part then needs to be designed to be bent and formed into its final geometry. So for example, you wouldn't be able to, you'd be limited by the type and the amount of complexity that you can put in that part without adding other parts. And that's what's done often, in chassis assemblies or components within the vehicles. You might combine multiple sheet metal parts together to create these very complicated geometries. So there's significant limitations when it comes to the manufacturing process.
So obviously it seems like there's a lot of limitations. In the future, how do you see a technology like 3D printing coming in, helping to mitigate some of these issues, and in some cases it seems like completely get rid of some of these issues that some manufacturing processes have?
Yeah, so additive manufacturing, 3D printing is not without its own limitations as well. But what we're able to do is break down some of those barriers. So additive manufacturing allows you to attack more complex geometry in single parts. Instead of having to combine multiple parts into an assembly to solve your engineering challenge, you can now combine all of these parts into one part and print that part. Now that allows you to remove fasteners, it allows you to simplify the number of parts that you need to control, and really, complexity is a friend of 3D printing, while complexity might not be where you want to go with other processes. So additive, number one, allows you to combine parts together. Number two, it eliminates the need for any type of tooling. So where you design a component, you invest in that tool, and then that tool sits on the shelf until you need it to make parts. In additive manufacturing, you have a soft tool, a tool that sits in your server and remains flexible. Even when it's design locked, it's still something that you can load and unload into the printer very easily. You can modify, and you can create a new tool very quick and easy. So there's these barriers that additive knocks down, but then there's also rules that additive must follow as well.
Cool. So, I mean, that all sounds great, but is this something that's actually being used today? 3D printing is sort of still up and coming in many ways. So is it something that's actually being used in the automotive industry today?
Yes, absolutely, absolutely. And it's interesting because you and I look around at the vehicles that we drive and that we have access to, and we don't see any 3D printed parts. There's a lot of metal parts, but none of them are 3D printed. But that is just today. What we're seeing is this tip of the iceberg forming, and what is underwater and what we don't see is all the use cases that are currently happening behind the scenes. And one of the biggest areas that 3D printing is being used in is the motorsports field. Okay, motorsports is an incubator of technology. The reason why Mercedes and Ferrari and Porsche and all of these big brand names tie their names to motorsports is because they incubate technology there that then eventually makes it to the road. Batteries was one example. And so over the course of the last 10, 15 years, battery technology has been evolving in the motorsports domain, and with the intention of bringing that technology to the road. And that's starting to happen now. You're starting to see hybrids and electrics come forward, and they've learned a lot about not only battery chemistry, but controls of the battery system, controls of the electrical powertrain. A lot of learning takes place there. And the same thing is happening with 3D printing, especially metal 3D printing, because that's functional, high-performance materials in the racing, in motorsports. And so a lot of teams in Formula One and WC Racing and Formula E are gaining performance through metal 3D printing. And the intention is to trickle that down into the road. And until recently, they've had no path to do that. There's been no way for you to take a component such as this water pump wheel, where you might make 200 of them for your DTM series car. This is what BMW does. This is a great example of where motorsport has used 3D printing to improve their technology. So a BMW DTM series car will boost its performance by 3D printing its water wheel, but to take that same design to the road and put it into a 3 Series or a 5 Series or a 7 Series car, you're no longer making 200 of them. You need to be making 2 million of them. And that's a totally different level of manufacturing, one that there hasn't been an answer for in additive manufacturing until now. If you could do that, if you could bring the cost down, to a tenth or a hundredth of the price of that part, you could put it into a road car. And so that's what the story that all of these OEMs and these automotive brands want to tell is born on the track, now available in your vehicle.
Cool. So talking a little bit about that, you mentioned the bringing it from the race car to the road, and mass production is kind of a difficult nut to crack for a lot of people. But where in that product life cycle, so from prototyping, mass production, aftermarket replacement parts, as far as Desktop Metal in particular, where does the technology that Desktop Metal is building fall within that spectrum?
Sure. No, it's a great question. So Desktop Metal has attacked the entire space from concept all the way through mass production, and then sustaining engineering, including aftermarket, after the vehicles are in the field. And the way we did that is by launching two products. One, the studio system for low volume production of either prototype parts, jigs and fixtures, or tools. And then another, the production system for high volume, sustained manufacturing and mass production. And the two of those working in concert can cover the entire spectrum of needs from the automotive space. So let's talk about, when a car is born, when the design starts. Nowadays, when a new model is being conceived of, engineers might take the old model and modify it. They may produce prototype components, mount new motors, new mechanisms onto an existing frame. To do that, you require maybe slightly different fixtures, mounting structures, and you need those to be functional. You need them to be real and strong. Because what you want to do ultimately is you want to put a mule test vehicle on the road. You want to test other mechanisms within the vehicle using new components. And so being able to print mounting jigs and fixtures that mount onto the vehicle is something you want to do out of metal. You want to do it out of something that is strong, heat resistant, corrosion resistant, and will last the testing duration on the field. Now you move into making new components. You can prototype new components out of stainless steel. You can print them on the the system. You can do low volume, tens, even 100 types of volumes to put test vehicles out on the field and test new designs, and not only the designs of those components, but the designs of the subsystems and the vehicle themselves. When you get into the shop and you start to weld assemblies or build the vehicle, the shops, the factories, the labs are using the studio system to create the fixtures that help to assemble the entire vehicle. So even if you're welding two pieces of sheet metal together, one of the most important steps in a sheet metal weld is to hold these parts together very strong. And these clamps, these jigs are unique to the new designs. And so factories are printing those jigs and fixtures to help them assemble. Now, once you've gotten to the point where now you want to invest in the design in the future, you start to look at tooling. You start to say, okay, now I don't want to make 100 vehicles, I want to make 100,000 vehicles, or 100,000, or 1 million vehicles. You can take these same designs that you've been working with on the studio, you can push them into mass production on the production system. Production systems gives you the ability to use the same materials, but at a much higher volume, 100 times the speed. And what that speed does is it reduces the cost significantly. So now you can pick and choose different components that make sense to 3D print. And I'll say that because not everything in a vehicle makes sense to 3D print. There are 30,000 components in a vehicle, and there might be 100 to 1,000 that really make sense to 3D print. But what that does is it gives the engineer another tool to design with. When they design a component, they can think, how do I want to manufacture this component? Do I want to cast it? Do I want to stamp it? Do I want to press it? Now they can think, does it make sense for me to apply additive manufacturing to my design? And what limitations do I have? What limitations do I overcome by doing that? So as we see more and more components being printed into vehicles, we're going to see more flexibility in those designs. So the engineers will have to invest less in tools, and they'll be able to change and modify and improve the design quicker and easier as they move forward. Then after the vehicle is launched and in the field, we start to see the ability to 3D print replacement parts, aftermarket parts, both for existing vehicles like new vehicles, where you may want to change things to make it your own, mass customization of your vehicle, putting your initials or your ideas on the vehicle itself. The Mini Cooper gives you the ability to do that now. If you order a Mini Cooper, you can print your own little dashboard variations. So we're seeing that starting to come. What the studio system allows you to do is print metal components, functional components for your vehicle, aftermarket that work like the like the original component. And in fact, older vehicles like classic cars. Porsche Classics is a great example, are starting to 3D print replacement parts for these vehicles that are very hard to find. And so what we're seeing is this broad adoption from concept all the way to end of life, where 3D printing can add value along the way.
Awesome. So digging in a little bit more to that, kind of breaking it down, you have the prototyping stage, you have this mass production element, and then aftermarket. I think we have some examples here that speak to those in particular. So for example, these are shock absorber pistons. So can you talk a little bit about why this would be a good candidate to go in and 3D print for prototyping?
Sure, yeah, and not just for prototyping, but this is a great example for why you would use 3D printing in general to solve problems. So shock absorber is a complicated hydraulic piston where basically you're creating resistance through a fluid by introducing channels and flow and tortuosity into the part. So this piston basically goes up and down in a fluid, and the fluid flows from one side to the other. Having the ability to really engineer those flow channels gives the engineer design freedom to put exactly the response that they'd like to see into that suspension system. If you are limited by the way you manufacture this part, like for example, this could be a traditionally manufactured press and sinter part, which means that the part is created by pouring powder into a mold and pressing it and then sintering it in a furnace. That's very common in the automotive industry. They've been doing powdered metal work for 100 years. In that type of design, you're limited to geometry that can be pressed by a die and then can be removed from that die. It's called a 2.5D, not fully 3D, but 2.5D manufacturing. And so these holes would have to be in a vertical position, and you'd be very limited on the geometry that you could use. If you wanted complicated geometry, you could come back and machine it, but if you also wanted flow channels that were doing some very creative things to create that tortuosity, you really couldn't you couldn't create them any other way than to 3D print them. So this is a great example of the way that engineers are really taking 3D printing and turning it into better performance.
Awesome. And then on the sort of mass production side, we have a few parts up here from our production system. Can you talk a little bit about maybe why these parts would make sense either from a size perspective or some other use case perspective to 3D print?
Yeah, so there are a lot of small metal components in a vehicle. And I mentioned earlier, 30,000 components, only maybe 10 to 1,000 or 100 to 1,000 are 3D printable. And those, right now, the ones that are being attacked are the low risk items. So let's say like switch rockers or brackets that kind of hold interior components together. Those are the low hanging fruit for automotive companies when they start to really want to test and engineer with a new manufacturing technology. So additive manufacturing of small metal components in the vehicle represent a way to reduce cost, reduce lead time, reduce tooling, improve performance, but also it's possible to do these in a very low risk way. So something that's not going to make the car dangerous. I'm not going to put a whole lot of risk on the automaker by designing components that are critical for the car's operation. It's very different than putting components in aircraft, for example. GE has been printing jet engine components now for 10 years and is finally starting to fly some of them because it takes a long validation period. In the automotive, we can take small, non-critical components and really take a lot of cost, complexity out of them very quickly.
Awesome. And then as far as the aftermarket goes, so I know like this guy here is actually of a vintage Mercedes. So can you talk, I know we mentioned a little before, but can you talk about going through figuring out what kind of parts might be good to print from an aftermarket perspective and how this kind of impacts how somebody like Mercedes could store their classic cars and their classic car parts?
Yeah, absolutely. When you get into classic cars, it's a fascinating business because the tooling for rehabilitation often doesn't exist. So it's very frustrating as a collector to go searching for junkyards and to searching around the world for components, especially non-critical components that just kind of are the final the final piece of the puzzle for these classic restorations. And this one by Mercedes is a great example. This is a thermocouple housing, very simple, but needs to be made out of stainless steel, and might be something very difficult to machine. It's meant to be cast. Those casting tools don't exist anymore. And so putting this on the studio system and printing it very quickly gives restoration teams a chance to fill these, to complete their projects. And in fact, I mentioned earlier, Porsche Classics is a great example where they've taken this to the next level. They've really put a business around it, and they're offering it to their clients, their customers. Because at the end of the day, Porsche has this information, right? They have these digital files. They might not have the tools, they may not have the ability to put these, even if they do have the tools, to put them into production and make components. But what they do have is they're starting to bring on 3D printing as a competency within the Porsche organization. And they can take files from the past. They can create digital files now of something that might exist only on paper, and they can offer that as a service or as a sale to a classic car restorer.
Great. So it sounds like there's definitely a lot that can be done across sort of the product development life cycle. Looks like there's a lot of more interesting things that this technology can unlock, not from the step one of just being able to print something in metal, but kind of what it can do for a company, from a business standpoint. So can you talk a little bit about, some of those things that 3D printing kind of unlocks, we'll say, for a lot of different manufacturers?
Yeah, so if you look at the very early stages of design, and when you're starting to choose a manufacturing process, and that manufacturing process then ripples through the part design throughout the vehicle, additive manufacturing represents an ability to reduce the number of parts, reduce the vehicle weight, the vehicle size, and now as we're getting into more and more EVs and emission standards, it allows us to work together from mechanical, chemical, electrical perspective within the vehicle to reach these targets. Make the car have longer range by lightweighting it, by combining assemblies, removing fasteners and unnecessary components, really being more efficient on the way that we build the car. So there's complicated geometries. And a great example of that is the software that we make called Live Parts, which helps an engineer take a design that might be traditional and designed to be cast in a more traditional process, and turn it into a much more efficient design, one that is generatively designed to be more functional and not limited by the manufacturing process. This is an example of a piston head that was designed by Live Parts. Live Parts is a software. We just gave it constraints, and it formed its own geometry around those constraints. So optimizing geometry, certainly one. Optimizing supply chain. So what we've seen in the past 50, 60 years is this consolidation of supply in countries that have low-cost labor, maybe have a concentration of materials being fed into them. And what we're seeing happen is additive manufacturing begins to open that up to a more distributed model, one in which we can reshore manufacturing to the US, to Michigan, maybe even Detroit. And this is very important for the US economy. We want to bring engineering, technology, intellectual property back into the US and back into Detroit, and help revitalize and rebuild our centers of excellence there. So additive allows us to do that, and we can use the material in a different form. Right now, powder can be shipped around the world and distributed to these additive manufacturing sites. Metal powder is what we use to make these parts, and they can make the same metal powder can be turned into multiple different geometries. So we're seeing entire supply chains be reinvented. We're also seeing designs more rapidly evolve. So engineers will conceive, design, simulate the design in the digital space, and you can spend a lot of time optimizing that design in the digital space. Great simulation tools we have right now, but to take that digital file and validate it, you need to build the prototype. You need to build a functional prototype of that, and you need to validate the entire system. So how quickly can we turn that digital file into a physical file, and then test it, break it, optimize it, and repeat? That design process is happening much faster. But one that I'm really most excited about is the idea of the circular vehicle. So the World Economic Forum has published these initiatives to the world economy, especially the environment, to reduce emissions, but also to make vehicles much more sustainable, and they call it the circular vehicle. And that's the idea that you want to use recyclable, reusable materials in the vehicle. Instead of pushing a lightweighting process by taking metal and turning it into plastic, we're now seeing an initiative to take that plastic and turn it back into lightweight metal. And additive manufacturing helps you do that because metal is essentially infinitely recyclable, while plastics are not. Plastics you might be able to recycle once or twice. And so I think following those types of initiatives is going to be extremely important, for the environment.
Great. So talking to somebody, say we have somebody here who is in the automotive world, isn't really doing any 3D printing now, but is interested in trying to use this technology. What's kind of the way to get started? How do you sort of dip your toe in the water and see what it's like, test it out, and then potentially one day be able to, put a production, live part in a car one day?
Yeah. No, it's a great question. So I would definitely start with prototyping, right? So take your ideas and make them real by using the studio system to produce functional prototypes. These are prototypes that you can put into sub-assemblies and assemblies that will now allow you to test subsystems and other parts of your whatever your mechanism and whatever it is you're designing. This extends way outside of the automotive space. So what you'll find is as you go through engineering design cycles, that you're going to need certain fixtures and jigs and tools. These are now, it's possible to print these. So consider the studio system as a tool to print the tools that you need to do your job. As you evolve your design through a prototype, through a rapid design cycle, start to think about how you can take that design into a more high volume manufacturing space. So the studio system uses the same material as the production system, but the production system operates at about 100 times the speed. So now small parts are going to be cost competitive with traditional manufacturing processes at very high volumes. So where you might be considering a bent sheet metal bracket, consider printing a more optimized design, something that requires no investment in tooling, might be lighter weight, might combine multiple parts in an assembly and remove the need for welds, for screws, for rivets, and look at some examples that the automotive industry is giving us. BMW's roof bracket is a great one. GM's seat bracket is another great one. Look at these very organic, lightweight designs that are being proposed and introduced, and I think we're going to see more of them in the future. And how can you remove material, remove lead time, remove cost of tooling by looking at printing in metal to solve your problems.
Great. So now we'll take some questions from the audience. So if you haven't gotten a chance, please feel free to add some comments below the stream here. So first question, we have, when are the systems going to be available to the public?
Oh, it's a great question. I get asked that all the time, and I have great news. The studio system is available today at a very short lead time. Usually we can complete an order within 2 weeks now. So, please go, jump in on that before, as we're starting to fulfill, our orders for the next quarter, the next year. That lead time might change, but I encourage everyone who's looking at a studio system to get in on that right away. The production system, a little bit later. We've already started shipping the production system to our early customers and partners. We have one out in the field right now at a customer site, but the production system is going into automotive suppliers this year. So you'll be able to get parts produced off of these printers. And if you're looking for a production system, and I'd say, we'd be looking at delivery in 2020.
Awesome. So where do you anticipate the biggest benefits of 3D printing for automotive being? Is it in cheaper products? Is it in better products? And if it is better, sort of what ways?
Yeah, it's really all of the above. I see, it's not every day that a new manufacturing process is invented, especially for metals, right? It's been decades since a new manufacturing method for metals is introduced, and I think that additive manufacturing in metals represents that. So the question is, where do we take this technology? Where do we apply it? Certainly to better designs, to optimizing designs and improving performance. But I also think there's a way that we can evolve materials using it as well. Because it's a new process, it's compatible with newer materials, and we'll be able to improve performance by introducing new materials as well. I also think that the potential for additive manufacturing is still in its infancy. We're seeing examples, but these are just, like I mentioned, the tips of the icebergs emerging, and behind them is going to be these flow of ideas that we can't even imagine right now, and applications that that we're just going to be blown away by.
Awesome. So kind of going off of that, when you're talking about materials, can you talk a little bit about the strength, stiffness, kind of the material properties of metal 3D printed parts versus other types of traditional manufacturing methods? How does it stack up?
Yeah, sure. So it's a really good point you bring up, and in fact one that I probably should explain. The performance of a material is very much dependent on the manufacturing method that you use with it. Take 3D printing and additive manufacturing out of the picture. If you take a stainless steel and you cast it, it will have very different properties than if you take a block of stainless steel and you cold work it and then machine it. Or if you take a piece of steel and you stamp it. That same chemistry of steel will have different performances depending on how it was formed. Now, powdered metallurgy is not different. It will have its own performance as well, and powdered metallurgy has been around for 100 years. Desktop Metal is using the same type of powdered metallurgy that we've been using for 100 years. We're just forming it in a different way, right? We're 3D printing it instead of pressing it, instead of injection molding it. So we have a very well-defined set of performance standards around powdered metallurgy. We understand how it should operate, and we target and meet those requirements and standards. So that being said, as you begin to design using additive manufacturing, you want to use the standards that govern metal injection molding and powdered metal to give you your performance standards.
Awesome. So how do you make sure these complicated, another question we have here, how do you make sure these complicated printed geometries have high quality surface finish? So kind of, how can you go about taking, a part that comes off the printer, either making that surface finish better or doing some processing to do so?
Well, so the great news about the studio system and the production system is that the parts that come off are identical to the parts that come off of casting processes or forming processes. The same density, the same metal, and so therefore the same post-processing techniques are available to you. And the reason why Desktop Metal didn't introduce a Desktop Metal polishing system or a Desktop Metal machining center is because all of those post-processing technologies are available and applicable to Desktop Metal printed components. For example, these parts can be put into a machining center and machined to very high tolerances and very high surface finishes. These parts can also be put into a surface finishing process like REM super polishing, where the part is basically dropped into a bed or a bowl of abrasive media and vibrated, and the surfaces are taken down from a dull, rough surface finish to a high shine polish. And the reason why you can do that is because the parts are very high density, and so therefore when you expose and remove the rough surface finish, what's underneath is a very high density solid surface. So the short answer is any and all post-processing, including heat treatments, hardening processes, are available to you from the printed parts.
Awesome. Yeah. The other question we have here, what are some of the design constraints on parts made on each machine, studio and production? Are they similar? And kind of what are those constraints?
Yeah, so there are design rules with any manufacturing process. And I think a misconception is to think that 3D printing is free of these design rules. You certainly need to have geometries that can be printed and it's supported during printing. And one thing the studio system allows you to do is build supports under these parts as you print them. So you can create overhanging geometries, but you can also create self-supporting geometries. So instead of having a part that is suspended at a right angle to vertical, if you angle that part at a 45-degree angle, then you can create self-supporting geometry and print it without those supports. Now the production system is slightly different. The production system prints parts in a powder bed, and so the powder acts as those supports. Now, what you need to keep in mind is that just because you've printed it without supports doesn't necessarily mean you can sinter it without supports. So a part like this that was printed in the production system doesn't require supports in these channels because of the powder that sits there. It becomes stable, but it's also self-supporting in the sintering furnace. Meanwhile, while a part that you might print with a 90-degree angle, it might be printable, would require supporting in the sintering furnace. And so there's subtleties like that. There's also differences between the studio system and the production system, where the production system is able to create, or I should say the studio system is able to create infill within the part that remains hollow. And it's because it creates this infill very much like an FDM printing process by sparsely filling the internal wall thicknesses and then capping them off completely. Now if you do that with the production system, you might trap powder, and so you need to leave powder drain holes in those hollow structures where you can get the powder out before you then put it in the sintering oven. But there's subtle differences between the two processes, but the nice thing is they both use the same exact material and give you the same properties.
Awesome. So how does part shrinkage affect the final dimensional accuracy of parts?
Yeah, so most of our tolerances come in due to the shrinkage of the part. Printing is very accurate. So for instance, take the production system, for example. We print at 1200 dots per inch, or DPI. Very high resolution images create the green parts in the powder bed. But when those very high accurate parts are put into the sintering furnace, the part shrinks, and it shrinks by up to 17%. That's all taken care of in the software, but there is tolerance with shrinkage, and the tolerance is very similar to that of a casted part. So if you think of a part where you might pour cast it, it's taking the molten steel, putting it into a die, and that molten steel then turns into solid steel, and there is a shrinkage that takes place when you switch from liquid to solid in steel, and that adds a tolerance to the production process. Think of printed parts as similar to the cast parts, where you can use them straight out of the printer as is with casting type of tolerances, but then you can always machine those surfaces to much higher precision.
So I think that's something we see a lot too, right? Like taking a part like this, which the tolerances might not be exactly what you needed, but you can take those critical surfaces and post-process them to fit the needs.
Yes, and that's it's actually a very good point that in most cases, the most critical surfaces of a part are going to be the easiest to machine. So in a water wheel like this, where if you machined this out of a block, you would spend 80% of your time creating these features of the fins inside of the part. And those features can tolerate significant geometry changes. The outer diameter and the inner bore are the easiest to machine. You put them on a lathe and you turn the part and you create a nice surface, whether it's on the inside or the outside. Those are the easiest to machine. and they're the simplest. So when you print a part like this, you can get away with the tolerances of a cast part on the inside and turn around and machine the critical components and the critical surfaces very quickly and very easily. And in fact, that's what we're seeing our customers do. Our customers are recognizing that, and they're saying, well, instead of starting with a billet and machining everything, I'm going to create my billet on the printer, and I'm going to then fine tune every critical dimension just by putting it in a very simple machining operation. And it cuts down 90% of the machining time.
Awesome. So it looks like we got a few questions on material roadmap. Titanium, carbide, aluminum. Can you talk a little bit about each system and what materials are available now, what's coming in the pipeline, and kind of what to expect there?
Yeah, so titanium is a really exciting material, and it's perfectly compatible with our process. However, when you get down into mass production of any material, the cost of that material begins to dominate the cost of the parts. And so as exciting as titanium is, as you start to pull out all the rest of the cost of the machine, of the time, of the process, which is exactly what the production system does, it makes making the part very, very efficient. You start to see the cost of the part being dominated by the cost of the material. And so unfortunately, titanium is still an expensive material to put into a vehicle. It's a great material to put into medical devices, into prosthetics, into surgical implants, because that type of application can shoulder the cost of that raw material. But it's a tough one to apply to the automotive industry because it would take a part like this and it would double its cost, which is unfortunate. But in some applications, we'd like to see it, and so we are developing. So titanium is on our roadmap, and there certainly are applications that we want to offer titanium. Hard materials like carbides and those alloys, very excited about those. They are perfect for the sintering process that we use, forming the parts in a green state out of powder and then sintering them. So hard carbides are very compatible with sintering, and so we're excited to introduce those types of materials as well. And then aluminum alloys. Aluminums are absolutely on our roadmap. I don't know exactly when we're going to launch aluminums, but it turns out that aluminums are an easy material to machine. And so our customers, as they begin to evaluate when they would apply additive manufacturing, you would apply additive in areas where subtractive is very difficult. And when you take a block of aluminum and you can machine it very, very quickly, compare that to printing the aluminum, you know, the benefits are not as great as if you took a really hard tool steel that is very difficult to machine and you printed that. You get a much bigger bang for your buck on that. And that's why we've introduced the hard materials first.
Awesome. So how long do you think until 3D metal printed parts can be used on those critical components in an automobile? So, you know, take kind of that connecting rod down there. You know, how long do you think it's going to take till we get to a point where somebody's comfortable putting that in an engine and running it?
Yeah, I think with any new manufacturing process, there is a validation period. And in the automotive industry, that validation period can be many, many years, in which the parts are tested at the lifetime of a vehicle, right? Accelerated lifetime testing can last for many years with a variety of variations and design cycles. But ultimately what you're trying to do is put designs in place, break them when you know they're going to break, be able to predict the failures, and then design around them into parts that don't break. I think we're very close to putting powdered metal into more complicated designs like this because the automotive industry is very familiar with the performance of powdered metal. We've been making gears for transmissions out of powdered metal for a long time. Gears that look like this are often pressed out of powdered metal and then sintered. And the reason why they choose to do that is because that's a very inexpensive way to manufacture a gear. You build a tool that is the shape of the gear, you press powder together to create the gear, and you sinter it in the furnace. Very simple, very fast, and very cost effective. And the performance of that powdered metal is very similar to the performance of the powdered metal that we print. In fact, our parts are more dense than those standard powdered metal pressing operations. And so the performance of our parts are actually greater than that. So as we begin to put use cases in place and see and prove that the performance, it creates parts that have equal or better performance than the parts that the automotive industry is already using, I think we're going to see this huge takeoff in printing parts instead of creating more and more tools and dies.
Awesome. So another question here, what 3D file formats is the Studio system compatible with?
Yeah, so that's a great question, and the answer is any and every 3D file format. So that's one thing that's nice about working today in 3D printing is that file formats for 3D printers have been standardized. And so we're able to not only take those standard files, but we're able to take in any file from any CAD system. So send a native SolidWorks or a native Parasolid or a native Siemens file. Any one of these CAD systems can send a native file to our printer, and our printers can handle it. Our software is intelligent enough to translate it into the file format that the printer takes. Then we take care of the scaling and the build prep, and then you're off and running.
Awesome. So kind of a similar question to one before, but how long until 3D metal printed parts do you think will be on sort of chassis frame components of a car? Is that something, what's the outlook look like for that?
Yes, so we're already seeing metal components printed and being placed onto the car frames. The entire frame, now that's a different story, but components of the frame, absolutely. If you look at the knuckles where frame components come together, where potentially tubes attached to each other or sheet metal forms are welded together, those assembly or attachment points are perfect candidates for 3D printing because they're very complicated and they often change sizes and shapes depending on the beams that come in and attach there, and they're often made of multiple components. So, for example, a corner knuckle of a frame might include 12 sheet metal stamped parts that are all welded together to form a shape where 3 beams can come together. We're seeing those being printed right now. Matter of fact, there are vehicles being shown as demonstration vehicles where the entire frame is 3D printed. In fact, the entire frame is not 3D printed, it's the knuckles, it's the connecting points that are 3D printed, and the rest of the frame is tied together with very simple tubes, either carbon fiber or aluminum, and simplify the entire assembly. So we're already seeing that.
Awesome. So another question here for the production system. Do production system parts have porosity due to the powder production method, or is it 100% filled solid after sinter? Yeah,
so it's a great question. And it's, I want to be very clear and specific that the final parts we call fully dense are fully dense to 99+%. But the reason why we say 99+% is because there are small voids throughout a part like this. And those voids are very common in all manufacturing processes. When you pour cast a part into a die, it can trap bubbles, it can create these small voids, and in fact they get bigger and they're more prevalent in a casting part. When we print parts on the production system, we are laying down an image of ink, essentially a glue, on a fully dense, and I call it fully dense, but it's a sheet of powder. So we're creating an image on that sheet of powder, and then we're gluing it together to the sheet above it. And what you end up with is a brown part that is fully packed of powder. When you put that into the furnace, all of those voids in between the pieces of powder are driven out of the part, and they're driven out to 99+%. That means that there are small voids within the part, but this is very common, and it's taken in consideration in the way that we design and the performance of the parts.
Awesome. So another question here, if you had to guess, is adoption for metal 3D printing going to be driven top-down from the supply chain side of things, or bottom-up in specific pockets, applications, kind of that way?
So I think both, but at first it's going to be top-down. What we're seeing are automotive OEMs who want to take advantage of additive manufacturing in their designs. They want to learn about the limitations of it. How can they drive cost, drive complexity out of their vehicles by using additive manufacturing? And so they're the first customer, right? We see OEMs forming centers of excellence, like what Ford has done in Detroit. They're exploring with all of these additive manufacturing techniques, not because they want to mass produce metal components for their vehicles, but because they want to understand it. They want to be able to teach their engineers the limitations of the process, the performance of the components that are printed, and then they want to push it on their OEMs. I'm sorry, on their tier ones. And when they push it on their tier ones, they will now know how to design for the parts, and they will know the process capability of the parts and the performance capability. But I think even more importantly, they will know the cost, and they will understand the cost targets that they can reach when they push these on their tier ones. So the tier ones are standing by and saying, what do you want? What do you need? We'll do it. We'll do anything you want. And the OEMs are now pushing that onto their tier ones.
Awesome. So another question here. How are you addressing the post-sales support for this product? Is there a channel for inquiries after purchase?
Yes, absolutely. So Desktop Metal has set up one of the most extensive sales channels in the world, and that channel is a support channel as well. And so you can rely on your sales partner in your area who sell you a studio system to be your support, your single point of contact for that printer. And it's a very similar structure that you may be used to for with your other 3D printers if you buy other 3D printers, or for your CAD software if you're buying CAD software. So what Desktop Metal, we're still a small startup, but we have a huge channel around the globe to help support you as a customer as you buy the studio system.
Awesome. Another question here. Given that the process is similar to metal injection molding and to the powder metallurgy, is the shrinkage comparable? So do we look at the shrinkage in a similar way?
Yes, absolutely. We look at the shrinkage the same way. So metal injection molding is it's a relatively new manufacturing process. It's about 40 years old. Metal injection molding was evolved into a very stable production method because they were able to tune in the shrinkage, essentially making the shrinkage reliable and repeatable. And that's the key. If you don't have reliable, repeatable shrinkage, you don't have a reliable process. And the way they did this was by using certain sizes and particle size distributions of powder. And so we've done the same thing in our printers. We've designed the printing process around powders that have reliable and repeatable sinterability. So they pack very uniformly when they're in the powder form, and they drive out porosity very uniformly during the sintering process. And because of that, you get the same type of repeatable and reliable shrinkage process as you do from metal injection molding. So you can think of us as leveraging decades of technology development in the MIM industry.
Awesome. Well, it looks like that's about it. So thank you very much for sharing a little bit of your background and your insight in the automotive industry. To everybody else, feel free to check out the Desktop Metal Resource Center for any more information, whether it's into data sheets and on the materials and things like that, or just kind of more information about overview about how the studio system or the production system works. That's all in the Desktop Metal Resource Center. So we hope to see you next time.
Great. Thanks, Nick.